Now let me pull the cable. No, that doesn't work. That's simple.
So what was it? Made it work yesterday? I forgot.
I just pulled the cable. Tried it now, but that doesn't seem to work.
Sometimes unplugging work more than it works.
Supposed that the chairperson never stand up.
Let's try another input.
I already changed it in TXT for HTML. This one? No.
Oh yeah, I got it. Yes. No. Jesus Christ. No, there is no contact. At least I keep it like this. Yeah, but I mean, fine. Oh, good. So what did we do yesterday? We look at the problem of electron transport, and with some sweat we can prove that it's all about scattering. In simple words, there is a certain number of electrons coming to nanostructure period in time, and some of them with a transmission chance do not pass the structure. This forms a current. Okay, such way of reasoning implies that the transport is indeed a stochastic process, right? We are talking about individual particles which go through the junction. In that case, we can think of assessing counting statistics of these particles. All right. To understand what I mean, let us learn how to count correctly. Suppose we have a stochastic process which has timeline, and we are talking about discrete events. How to characterize statistics of such events? All right, first of all, you define time window, delta t, in this plot. And then you must be ready for quite some dull work. Namely, you just count number of events within the time window, and that gives you one random reading. Then you build a histogram. You plot the number of counts for each number of events. It takes quite some time, quite some many measurements to build such a histogram. What does it show? First of all, from this histogram, from this probability distribution, we can understand what's the average current, and then the spread of the distribution. It will give you a value of noise, an error. I don't know about now, but I presume we have all similar experience during our first months in physical studies. At some stage, you should make an experiment which gives you a notion of measurement and error. For me, it was a cosmic ray detector, which gave clicks, and I had to count rather stupidly the number of clicks in time window, write it down again, compute the average, compute the dispersion, compute the noise. Who has had similar experience? Okay, once again, sizable minority. Fine, good. When I was encountered, I was very romantic. It was first weeks in my studies. I still had very romantic notion of physics. I thought, I got such beautiful data. But I have to discard like 99% of this data just to derive the average. This data might mean something, and I discard this information. That was my impression. And then I learned from other people that one don't have to discard it. One could eventually build up the whole histogram of such events and learn something about stochastic process in hand. All right, so time window, probability to have n, in our case, electrons, not baby born, not birds, past a window, or we just count electrons. Let us see. I need to introduce some mass. Wonder if you're okay. So I have to, yeah. I don't want to talk about probability, rather I would like to talk about characteristic function. Who remembers characteristic function from probability course? It's a pity. It's a very handy concept. Characteristic function of a probability distribution, we don't talk about electrons, but discrete events. It's, roughly speaking, a Fourier transform of this distribution function. So we have probability which depends on n. We make it Fourier transformed with some whatever. I wouldn't call it wave vector, but there is a parameter in Fourier's transform which is called chi. Okay, that's the characteristic function. It's handy and usually discussed in probability course because derivatives of this characteristic function with respect to chi eventually gives you moments. Average value, second cumulant, which is noise, third cumulant, like this. So it's a representation of probability distribution. Another use, which is important for me, that the characteristic function factorizes for independent events. Probability does not. Probability is a convolution of different independent sources. And if you just look at the probability, you cannot really understand what events are dependent or independent. This characteristic function, it goes pretty well. For independent processes, characteristic functions factorize. Right. Now I make a jump which looks a very unlogical jump, but in fact quite obvious. Listen to me. From this fact, it follows that the logarithm of characteristic function at large times is proportional to time. Who can explain this? Who can connect these two statements? It's also a bit of probability course and some physics involved. Yes?
We assume two characteristic functions with them under the logarithm. Actually, now that for in this understanding, we can write two characteristic functions have two characteristic function multiplication. So that c, if we take the logarithm of that, then we get this logarithm total characteristic function sum of
Yeah. So first of all, log, it means that independent contributions at the characteristic function, the log of characteristic function. Second, what we have to recognize is that the events separated by large times are independent. Okay. Then if time is sufficiently large, we have independent contributions from one interval, second interval, third interval, and so on. All right? So the total sum will be proportional to time. Good. That's all probability. Let me give an example of application of this characteristic function. Let me show how could it be useful. Not for a physicist, because, well, who cares about physics nowadays? Let me give you example from zoology. Suppose we have a zoologist, whatever, how you call it, I'm going to say, it doesn't matter, a scientist in birds, right? Ornithologist, indeed. Right. And he or she just counts the birds which pass near his or her window, right? And the histogram is made, characteristic function is computed. And after a long while, there is expression for this characteristic function. Okay, this expression is proportional to time window as expected. And it has log. And what one finds under the log, one can expand in terms of exponents of I chi. This fact, exponent of I chi, if one looks at Fourier transform, indicates that the birds are discrete entities. Right? N changes by 1. Plus minus 1. That's why we have this expansion in terms of exponents. Right? So one computes from experimental data these coefficients, and what do they mean? All right, something about birds. There are single birds, and they pass window independently of any other birds. And that coefficient gives you a probability for a single bird. Next step, some birds form couples, pairs, and it's natural to assume that they fly together. All right? Again, this analysis provides a probability to have a pair. Moreover, the birds flock, make large flocks, which and them or all of them fly together. And that's also to be seen in this expansion, in this characteristic function. Okay, that's just an example how counting birds and extracting statistics, characteristic function, can be applied to derive conclusions about birds' behavior. Yeah?
I have a silly question, but so these coefficient W's here are then basically directly connected to P of n, P of 2, the probability that we started from.
It's not direct. One has to make Fourier transform. Yeah, inverse Fourier transform, then we return to to use histogram, right? But we don't want to go there. We went actually in the opposite way. First, we collected data. We obtained this. We made Fourier transform. We come to this. We look at its functional dependence. And then we get these coefficients. And they characterize something about birds. Right. Let's go to electrons. Let me give you two simple examples of electron content statistics, which we can actually digest almost with no formulas. First of all, let me consider tunnel limit. We've been talking about tunnel limit. What does it mean? There is very small probability of electron transfers through nanostructures. What does it mean? It means that only few electrons pass the nanostructure. It means that successes of transmission are separated by huge time distances. That means that they are independent, precisely. Right. So, in fact, in tunnel limit we have simple, it's called Poisson statistics of independent transfers. All right. In terms of this parameter chi, okay, log is proportional to proportional to this quantity, which just means that electrons go by one. For birds, it would mean that W1 is 1 and all other coefficients are 0. Electrons really go by 1. Well, it's easy to remember, it's easy to recognize. Let us consider the opposite case, which appeared to be rather non-trivial. Let us consider open channel. And it means that electrons just go without any reflection, without any scattering. Crucial point is to notice that electron is a wave. And if there is no scattering, this wave just keeps its wave vector, keeps its momentum. Momentum is well-defined quantity. It does not fluctuate. This means that in this situation we expect no noise whatsoever. And the number of electrons in time window is just fixed. That's it. So there are two limits: independent single electron transfers and the noiseless configuration of electron wave which just moves through the junction. What is in between? That's been one of the most interesting and splendid calculations in history of quantum transport, which is called Levitov formula. Levitov is a person. Right. Rather involved expression. But we can understand all physics if we recall what I told. For independent events, characteristic function factorizes so that logs of these functions are additive. All right, so we have the sum over two spin projections. It means that spins are transferred independently. We have integral over energies, which means that electron transfers at different energies are independent. We have sum over transmission channels. Again, it means that electron transfers in different transmission channels are independent. That's all fine. That we can accept. What is a bit difficult to accept, although it's pretty simple, but, well, requires some recognition. Electrons coming from the left and from the right. Are they independent? Well, from physical reasoning, one of the most important elements of physics is locality principle. Your fate doesn't depend on anything what happens in distant galaxies. Your fate is here now. Okay? You look like it's a very new concept to you. Anyway, locality principle. And here we have a violation of locality principle. In fact, one cannot say that electron transfers from the left and from the right are independent. They are dependent. This dependence can be presented rather simple in terms of blocking factors. What I see here in this formula is the combinations of filling factor on the left and 1 minus filling factor on the right. What does it mean for fermions? Electrons are fermions. The certain number of electrons coming from the left, they want to get to the right, but they have to find an empty space over there. That's why we have to the second blocking factor 1 minus Fr. Good. So fermion statistics, Fermi-Dirac distribution eventually provides answer and eventually breaks non-locality. Okay, then control question. Why fermions break non-locality?
Because we can distinguish them. Because we can distinguish them.
Yes, very good. And how does it work? Why non-locality is violated if we cannot distinguish electrons?
Well, if there are 2 electrons in one place and in another place, we don't know if this, they can change.
Right, for fermions, a function of 2 particles must be asymmetric with respect to exchange of coordinates, right? That's all we know. Right? Let us know that one electron can be in Japan and another electron can be right away. The wave function still antisymmetric, despite the fact that they don't talk to each other. They never met each other. Why is it so? Somebody knows fine formulation of this? Electrons are fermions. Wave functions to fermions is asymmetric with respect to exchange of coordinates. It holds for any distance between the particles. So one particle can be in Japan, another particle can be here. They don't talk to each other. There is an obvious, evident violation of locality principle. So why is it so? Yeah? Who was that Pauli who arranged it like this? No, you're right, of course. Why it's Pauli? Why there is Pauli principle? Okay, the answer which I know is very fundamental. It's unbelievably fundamental if one takes this setup of electrons going through the junctions. That's because there are no particles in nature. With no particles, we have quanta of a field, which is the same in Japan and over here. That's why non-locality is not preserved. We cannot talk about particles as local objects. So it's a field which is present everywhere in the universe. Good. So we have blocking factors. In particular, it means that if we have equal field factors, there is no electron noise. There is no electric net current. This isn't easy to understand. But if the processes were independent, we would always have noise. It would be the same number of electron transfers from the left to the right, from the right to the left, which would provide the noise. There is no noise. This is consequence of Fermat statistics. This is consequence of Pauli principle. This is consequence of the fact that there are no particles in this world, but only fields. Right. So let's leave it a formula. What I would like to, another point to stress, it's the only input which we need in this case is again transmission coefficient. So if we have scattering, matrix, we have transmission coefficients. We also know full counting statistics. Let me give a simple example. It was tremendous calculation by that time. It was edge of application of quantum mechanics. And perhaps the authors have been slightly disappointed that the answer of this calculation for a simple case you can explain to most of street hooligans. Right. How would I do this? Well, the certain number of electrons come into the junction. They come to the junction, and it works like a gambling machine. Each coming electron pushes the button, and he wins with a chance of T transmission. Then it gets through, then another member of the queue comes, does the same. All right, this simple concept eventually gives true answer for counting statistics of electron transfer. It's called Bernoulli distribution if one puts it into numbers. It's a characteristic function, Bernoulli distribution. But without formulas, you can explain the principle to any street hooligan. Right, let's reproduce the limits. If transmission is small, only few electrons can pass. The transfers are independent. If winning chance is 0, then we have all this Q uniformly going through the junction. There is no noise. Fine. So we've done with full counting statistics. Right. It's an example of non-trivial application of the scattering approach. And I will talk a little bit more about transmission coefficients. Yep.
Back to the previous slide.
Yep.
What are the symbols in the lower vending machine? On the left-hand side?
The same gambling machine. I just wrote it twice to indicate the channel where electrons go in opposite direction.
No, but what are the symbols?
It's E, but just for the
Okay. Let's first recognize that we can estimate the number of active transmission coefficients that are of the order of 1, just by looking at conductance of a device. Why is it, sir? Each channel could provide us conductance of conductance quantum. All right. So if we just take conductance which we measure, divided by conductance quantum, we will have estimation of number of channels. Good. If conductance is of the order of conductance quantum, there will be one channel. Let's take a sample of big conductance. Then, if I plot all transmission coefficients as lines, I will have such a sequence of lines, which looks like a code. Just for fun, I plotted this for a diffusive conductor with resistance of 50 ohms. So one can see several hundreds of different transmission eigenvalues, which are spread from 0 to 1. If I would like to manufacture the same conductor, I won't be able to put all impurities, all scatterings at the same position. So there will be another value, other set of values of transmission distributions. I did twice. At least at the present level of technology, when we cannot shape the world atom by atom, we would never able to make completely similar nanostructures. Like when you make kids, you cannot make them identical to yourself. But nevertheless, you can produce a kid which is of certain class, certain ancestry, with certain characteristics, which comes in a certain type. All right, that kind of what I mean by showing these pictures. So individual set of transmission eigenvalues is a characteristic of individual nanostructure. Like your pin card is individual characteristic of yourself. What will characterize the type, the class? This is distribution of transmission eigenvalues. To do this, I just, if there's sufficiently many transmission eigenvalues, I just count their number in a certain window of transmission eigenvalues. So I have a function of transmission eigenvalue, which is, by the way, plotted here in a pink line. So we have enhanced probability for low eigenvalues and for high eigenvalues, transmission eigenvalues close to 1, which is, by the way, typical for diffusive contact. There is a formula for that, which displays divergences at small and large transmission eigenvalues. Okay, we will talk a little bit about distribution of transmission eigenvalues. Is the concept clear for you?
Why is it non-normalizable?
You don't have to. Let us recall some considerations yesterday. If one just integrates this function, one gets the total number of channels. But as we have heard, there could be zillions of channels coming to nanostructure, while only 3 or 4 eventually pass. Better normalization would be to integrate it with T, which would give you conductance. But, well, conductance it also fluctuates. It depends on from sample to sample. Normalization doesn't make much sense in the theory of quantum transfer because the number of channels is not very relevant quantity. One shall count channels which contribute to conductance. Yeah. In this case, propagation of electrons is such that it does go through the junction. Rather, it experiences many scatterings And the element inside the junction goes back and forth before leaving the junction. It's kind of simplest definition of diffusion motion. One could also write diffusion equation for that, but let it go like this.
There could be a more complicated junction where you need more parameters to write down the transition.
Let me show that. Let me give two other examples of transmission distribution. Okay. If we have tunnel junctions at most transmission coefficients would be close to 0, let's have not a very ideal tunnel junction. Let's have some impurities aside. Then the distribution would be something like that. It will be concentrated at low transmission eigenvalues. Let us take quantum point contact and let us make it a little bit realistic, like in the experiment I showed to you. Right? Then in this case, one should not expect that all transmission coefficients are strictly 1. Rather, they fluctuate in some window. So there is an example of transmission distribution for realistic quantum point contact. Again, the distribution characterizes the type of the contact, while all these lines characterize individuality of the structure. Yes?
Can you elaborate on why there is fluctuations in the transparencies? Is it just due to the imprecise fabrication, or is it something else?
Right. One can say it's not fundamental because it characterizes present level of technology. We cannot really make contacts with atomic identity. From the other hand, I guess we have to cope with this for like 200, 300, 400 years. So let's call it fundamental for time being. Good. Then, if no more questions, I'm done with lecture number 1. I'll go to the lecture number 2. It's very risky, but I will try to disconnect it. Yeah, get it back. Great. So, second lecture. It will be about quantum interference, but not quite right away. First of all, I will have a rather boring topic, because in order to talk about interference in the context of scattering, I will have to talk about multi-terminal scattering matrix, multi-terminal situation. That will be simple, well, it will be perhaps rather boring. At some stage, I will come to beam splitter, which I will need. And then, finally, I can get to interference and manifestation of interference in quantum transport. Okay. Let me try to go through this piece rather fast. Stop me if you are not satisfied, okay? Oh, good begin, yes?
The difficult formula, could we take into account the interference of incoming and right coming and left coming beams?
No.
So we assume that it will be averaged out in large time scales.
One doesn't have to take into account, because everything which concerns interference or whatever is already incorporated into transmission coefficient. Once one has transmission coefficient, one can forget about all underlying processes which form this transmission coefficient. All right, but yes, that's basically the topic of the lecture, how to compute transmission coefficient if there are several nanostructures present together. So, multi-terminal conductor. We consider 2 leads. Let us consider more. How many leads do I have? 1, 2, 3. Perfect. Next to it, just not to confuse you and to bring it closer to experimental situations, I would have some electrodes which are not leads, gate electrodes. So there's capacitor which shows there's no direct current can go through, right? With this you can shape nanostructure, change the properties, but as far as transport is concerned, I should have leads. So I have 3 leads. I can keep it at different voltages. I have 3 voltages. And that is action. This is what I apply. And there is reaction of nanostructure. What is the reaction? The currents, precisely. Here they are. The nanostructure reacts, giving currents to each lead. The currents conserved. That's, by the way, one can easily assess small nanostructures, right? Nanostructure is small. The lead is a million times bigger, wider, contains many, many atoms. Nevertheless, the current in this lead, by magic, is the same as in the nanostructure. Current conserves. Good. Let us see how we can define scattering matrix for such a configuration. Precisely in the same fashion. The only point one has to understand that incoming waves can come from any lead. Outgoing waves can go to any lead. It is perhaps handy to have double index for each mode. Right. The first part of the index shows the terminal. Second part of the index shows the number of channels in this particular terminal. This element of scattering matrix just shows amplitude of propagation, where particle starts in terminal alpha, in channel N, and ends up in terminal beta in the channel M. These amplitudes form scattering matrix, and again there is a property of unitarity, as it should be. Now I just rewrite it in terms of blocks, so it became a little bit fancier. Good. Again, as in case of 2 leads, there is a symmetry with respect to time reversal. How will I express it? And indeed, it's about a movie. One can watch this movie in one direction or another direction. It should give you the same. So, if time reversibility holds, the matrix must be symmetric with respect to index exchange. All right? Time, symmetry, and its violation is usually associated with magnetic field. If one changes sign of time, magnetic field also changes the sign. That's why this formula. All right, so basic properties are the same as for 2 leads. Right, so currents. Let us assess simpler situation when voltages are small. So currents are linear functions of voltages. So we introduce conductance matrix. What does it show? It shows the current in index K, in channel K as a function of voltages. 2 very obvious but fundamental properties of this conductance matrix. First of all, there is no charge production in the nanostructure. It means that at all times the sum of all currents from the nanostructure must be 0. Good. That implies that in any case, summation of this matrix is 0. All right. What happens if one sums it over second index? Well, it is also 0. Its explanation is written as transparency, but perhaps not in obvious way. Who can explain why summation of a second index gives you 0? Right. Who has not read it but is able to explain? You have read it. You have read. Yeah. If all voltages are the same, if you shift it by equal amount, you produce no voltage differences, which means that you produce no currents. Fine. Good. So what we know what is to compute first. Yeah. Oops. No. Just to show that for two leads, it's the same property. The only point that I would have to write 2 by 2 matrix with these elements if I really want to make it consistent with multi-terminal geometries. Usually one should not do this. One conductance is pretty much enough to describe the situation. Right. Let me talk about Landauer formula for multi-terminal structures. In this case, instead of transmission coefficients, I would rather introduce probabilities, P alpha beta. What does it mean? It means the probability to start in the lead, let's see, beta and go to the lead alpha. That allows us to understand the first term. Look, there are some electrons coming in the lead beta, they go to lead alpha, they produce current in the lead alpha. Oh, there's a second term. Who can explain the second term to me?
There are current in this source and there are current from this source.
Let's look at it. First, we look at the current in the lead alpha, and we see that it depends on the same fill-in factors, which means that something which doesn't involve all other electrons. It must be, in fact, reflection. Right? It must be reflection where electron starts in channel alpha and goes back. But what I have here doesn't look like reflection coefficient. It involves all probabilities. So what's the problem? There must be reflection coefficient to channel alpha. But the sum of all probabilities is 1. That's why I can express it as a sum over probabilities to all other channels. That's it. Simple matrix. The probabilities I can express like this, the same as for transmission coefficients. It's just products of the amplitudes. I have to take trace, which means that it is a summation over all possible channels in each lead. Good. I'm done with Landauer formula. One could also write down Levita formula, but it's too much involved. I wouldn't bother with this. Fine. We have description of the transport for a multi-terminal structure. Let's turn to concrete examples. All right, that's how one can compute conductances, but yeah, it's pretty trivial. Let's turn to concrete examples. Let's talk about beam splitter. Beam splitter, simplest multi-channel structure. It has 3 leads, 3 incoming waves, 3 outgoing waves. So the scattering matrix is eventually a 3 by 3 matrix. What I put here is a very special beam splitter, very convenient for our optical so-called friends. It is symmetric beam splitter. Let's see, what does it mean? If incoming wave comes from electron number 3, it is equally spread to terminals 1 and 2. How one can see that? One looks at this row of the matrix. The coefficients 1 or square root of 2. We square it to get probabilities. Probabilities are 50%. And there is no probability of reflection. Okay. If you try to send the waves in these terminals, right, we have different probabilities. One can compute these probabilities. Really? What's the reflection probability if you come in channel 1? Reflection probability. Okay. Okay. Fine. Good. That we will need later for quantum interference. I have seen a poster with a beam splitter. Does it? Who's the author of this, also of this poster?
Yeah, I have this in my poster,
So does it correspond to your concept of beam splitter? Okay, good. Interesting point which kind of fascinates me, also very simple. It would be very handy to have a beam splitter which is completely symmetric, right? There are 3 terminals. You put waves, and there is no reflection, and the wave is equally distributed between these 2. Okay, but it appears to be as kind of an example of perpetuum mobile. One cannot devise scattering matrix with these properties, provided the scattering matrix is unitary. No way, one cannot make such a beam splitter. All right, let me go. One can compute conductance matrix, but let's skip it. Let's talk about double-slit experiments. There was once a rather stupid survey among the physicists. What is the most beautiful experiment in physics? And that's the winner. Double-slit experiment. So what we have there, let me talk about waves. Let me not to specify whether it's light wave or electron wave, whether it's quantum mechanics or optics. There are waves propagating from point A to point B through 2 slits. Right? There are 2 passes, here and here. And to get probability from going from point A to point B, one could not just sum up probabilities of the passes. Instead, one has to sum up amplitudes along these passes. Amplitude A1 and amplitude A2, square it, And only after that one gets the probability. What does it mean? It means that the total probability is a sum of two probabilities plus interference term. That depends on phases of the scattering amplitudes. The probabilities are just moduli, they don't depend on phases. Interference term manifests the phases of the scattering amplitudes. All right? Double-slit experiment. Let me go on. Let me talk about phase shifts, which can be acquired in the context of quantum transport. Let me keep it simple. Let us see. Let me first consider one-dimensional channel, and let me assume no reflection. Then one could say, well, it's boring, nothing could happen to this electron. Many things can happen. How come? In this case, wave function is just a phase factor, but this phase can have non-trivial dependence on x, which is very simple to compute. The local derivative of this phase is nothing but local wave vector. How do you define local wave vector? There is energy of the particle, there is kinetic energy, potential energy. With this, one defines k vector, and one sees that the potential eventually affects the phase of an electron, even if it doesn't scatter this electron. Fine. Let us talk about energy dependence of the phase accumulated when electron goes between 2 points. One differentiates this expression. One gets nothing but inverse velocity of the electron, which means that derivative of the phase with respect to energy accurately gives you transmission time between these two points. Right. Voltage dependence. Let us apply some gate voltage, so we don't really try to take this electron from nanostructure. We just affect it with electric field. All right. So this change can be estimated as voltage we apply times time of flight between these two electrons. All right. That's our shifted, the phase shifts due to potential. In this case, the shifts are the same for passes of opposite directions. Right? That's what I put. For reasons which are beyond my comprehension, these phases are called dynamical phases. Interestingly, there's another example of phase shifts. Which are acquired in magnetic field. Here I gave some derivation, which I would like to skip there because it's like elementary quantum mechanics plus elementary electrodynamics. The phase shift appears to know about vector potential of magnetic field and is given by integral over this vector potential along the contour, along the trajectory which goes from 1 to 2. If the direction of this trajectory is changed to opposite, the phase shift is also opposite, in distinction from dynamical phases. I would know how you would name this phase. uh, almost equally strange. Almost. Yes! It's called geometric phase. Again, you remember this, perhaps you can explain the reason for that. I cannot. But it is called geometric phase. Fine. Let's have a Aronov-Bohr setup indeed. Was a fascination of physicists like 6 years ago. Let's have a coil perpendicular to the screen. Let's have some flux in the coil. If coil is long enough, there is no magnetic field outside the coil. Let's have electron which can go around the coil, either taking this path or this path. Let's look at the interference of this electron. It turns out that this interference is determined by the total flux in the coil. So although there is no magnetic field which acts on the electrons, they somehow feel the presence of magnetic field in the coil. They feel vector potential, they feel the flux enclosed by this trajectory. This is Aronov-Bohm effect, and okay, it is proportional to this flux. Right. The proportionality coefficient, we have dimension phase, we have dimension full flux, and to get the phase shift we divided it by flux quantum, which, like conductance quantum, is made from fundamental units, fundamental constants. All right, that is the essence of Aronov-Bohm effect. We're still in the particle physics. Let me have it in quantum transport. Oh, I need to explain double junction first. So, postpone this. Guess we need the beginning of third lecture for Aronov-Bohm effect. Let me take a simpler example of interference. No magnetic field, only dynamical phases. All right, let us look at the setup. We have one junction with scattering matrix left, another junction with scattering matrix right. We combine a scatter from the two, and we would like to understand the transmission, the total scattering matrix and transmission amplitude in series. We will solve this problem very easily, but there is a very interesting trick with the problem. And by some chance, native Russian speakers have advantage of understanding this concept, because by some strange cultural twist, they've been told about this since they're babies. I don't know why. Good. So let me talk what they've been told like babies. Let's see how does it help. It's a riddle. The riddle sounds as follows. A and B have been sitting on a roof. A has fallen down. B has fallen down. What is there on the roof? You know that? Okay. How many people know their answer? Eh?
And not the Russian center?
Well, I don't know. You could have something, you know, in your blood, which will tell you. Okay, once again, A and B have been sitting on the roof. A has fallen down, B is fallen down. What is there on the roof? And and look, I'm deadly serious. When we connect these two conductors, we cannot just connect them as it is. We have to connect it with something. And this something has a new parameter has a new parameter, accumulated phase shift at this space. So and is really, really important here. One cannot combine two scatterers without mentioning and, without describing how do you combine them precisely. Okay, we understood this. After this understanding, the problem is trivial. We can just sum up amplitudes and come to the answer. Let us first consider very simple scenario of transmission through both junctions. Okay, it's plotted here. So there is a transmission amplitude through the left, transmission amplitude through the right. One should not forget this and. It gives you phase vector. So it's expression like this. Left and R. Does it exhaust the possibilities? Not at all. It's shown here. There is a possibility to reflect from the structure, to get back to the left one, to be reflected again. Okay, we just write it down. Left and reflection once again, and because one has to transfer this piece second time. Reflection from the left, transmission to the right. Okay, if one repeats these bounds, one understands that any time for any bounds, one just add a constant factor to the amplitude. So in fact, we have the problem of summation of theories, which are also called geometric. It has nothing to do with geometric phase. Take a notice of that. Yeah?
Is it the same phase factor going from left to right and right to left?
Yeah, at this particular example, it's the same. There's no magnetic field. The phase is dynamical, so it is the same. Fine. We sum it up. If we have a formula, now we have to square it and discuss the properties of this. Let us see. Yeah. Here I wrote the formula with full glory. It depends on phase shift between this conductors. So now I plot the result against phase shift. One of the reasons to plot it against phase shift is to say, well, it's a phase shift. It depends on energy, right? So one could think of a transmission coefficient as a function of energy or frequency. And at this moment, each French patriot should recall two names. Very good. Fabry-Perot. What we have now is a situation which is called Fabry-Perot resonance in optics. There are two mirrors which hardly transmit. But arranging them and having interference between two, one can achieve almost ideal transmission. Right? That's interesting. I could have two tunnel junctions in series. By properly choosing phase factor, one can achieve resonant transmission with coefficient 1. Right. In this case, if I look at the transmission, I see a sequence of peaks. It's almost zero everywhere except resonant transition. Well, I can regard it as a quasi-levels in the structure. At certain energies, there are bound states for electrons have been formed. Like in Fabry-Perot experiments, there are bound states for lights. Standing waves are formed at certain frequencies. All right, it's almost noon, so I guess I need to stop. So I could go on, but I guess it's time to... Really? Okay. Good. Then 50 of 15. Okay. Good. Fine. Okay. Then I have to decide on what to do because I didn't want to really talk much about all particular stuff. Let me discuss something technical but useful. We have solved this scattering problem with two junctions by doing what? We have considered individual trajectories propagation. We sum up over the trajectories. We got total amplitude. We squared. We got transmission. Okay, that was good for two junctions, but for more complex structures, it can become cumbersome. Let me outline more general method to solve such problems. The method is simple, and it is as follows. What one has to do is to find a wave function of scattering state. Let's see. I look at the left, I find scattering amplitude 1. I want to understand what's transmission coefficient. I also have reflection amplitude. But I also have wave function in the middle between two scatterers. So by these letters A, C, B, D, I noted amplitudes for two directions of propagation. All right? So it looks a little bit like, you know, that textbook problem about matching wave functions. But it's even simpler. What is in common is that one has to find all these coefficients inside the combined nanostructure. All right. It's all linear. Quantum mechanics, for some strange reasons, is a linear function. It's linear theory, and it's actually a big blessing. So we have to solve linear equations. We're pretty much skillful in linear equations, okay? Good. So in order to solve equations, we first have to make equations. How do we make equations? Each scattering matrix involved provides you with a set of equations. How come? Because this scattering matrix relates incoming amplitudes and outgoing amplitudes. What are incoming amplitudes? In this case, there is a wave with amplitude 1, this wave with, with B. So here it is, incoming waves.
You have reversed the A and R.
What?
You should change A and R. The A and R total. In the left equation, you should change A and R total.
No.
R total is reflected wave.
Let's see.
It's proportional.
First is reflected. It gives you a reflection amplitude, isn't it?
But according to this, it gives A.
Yeah, A is, yeah. Or B and 1 have to change that.
Let's see. If there is no. Okay. Yeah. Let's see. It's kind of a mix-up of reflection and transmission. So the transmission eventually occurs if one goes back. All right. But okay, it's a definition of scattering matrix. One can call reflection, transmission, transmission, reflection. In any case, it relates incoming waves to outgoing waves. For multi-channel structure, reflection and transmission is kind of even more confusing. Very good. So there is another scattering matrix. Again, it gives a relation between incoming and outgoing waves. In this case, one incoming wave is missed, 0 here. Okay, and the phase factor also can be regarded as a scattering matrix. Very simple scattering matrix. It's just multiplication of diagonal elements. So here we are. Good, we have equations. Now we combine equations. We solve it for unknowns A, B, C, D, and finally find T, transmission amplitude. So it's more automated method of solving the scattering problems. Let me remind you that in the draw box, one finds a variety of scattering problems, a little bit at this level, and all right, one can go through most of them, discuss it with me. Right. I still have 15 minutes, or is it? Fine. It's about Aronoff-Bohm effect. That's why I need actually beam splitters. Once again, what I want is to have this coil. So I have to encircle this coil with 2 passes. Right? But then I have to connect these 2 passes into a single channel. So I need 2 beam splitters for that. Good. So that's the simplest one-channelization of our Aronoff-Bohm structure. It involves 2 beam splitters. Let me sort out the phases. Now the phases are not the same for propagation in either arm in 2 opposite directions. They differ by geometric phase, which comes from vector potential. These phases can be chosen different way, provided the sum of these phases is related to the Aronoff-Bohm phase, which is related to the flux through the loop formed by 2 passes. Good. let me just mention something simple and perhaps less evident instead of giving all these formulas. There are interferences of several types. Let us consider different trajectories, the simplest ones. Here A corresponds to path in upper arm, B corresponds to the path in lower arm. They do interfere. They provide conductance which oscillates with Aronoff-Bohm flux. There are fancier trajectories. Let me consider a single example. All trajectories which I wrote are in fact equivalent. So trajectory C, it comes in, it makes a loop within the structure, is reflected getting out. If one compares C and F, these trajectories are largely identical. What is the difference? Cannot formulate it once? Yes?
Different values.
Hmm?
We have made circles around the flux, and here we
did.
in our
Both.
trajectory there is flux.
We did. For both trajectories, we got around the flux, making a closed loop. The difference is that we did it in opposite directions. That's the difference between C and F. Fine. Let's look, not the whole expression, let's look at the interferences of these two trajectories. Simple one. It's just double-slit experiment. So we expect interference term to depend on the phases. The phases are dynamical and geometric. So finally we have an expression which depends on both. Right, it's a periodic with a period of 2 times phi naught. What is interesting to note? Suppose there are many trajectories like this, and different trajectories will have different dynamical phases. So if there is a contribution from many trajectories, it's supposed to vanish because of oscillating nature of this term. If you average it over dynamical phases, it will go away. Good, it looks like interference should go away. Not, wait a second. Let us consider another example. Let us consider an example of these two trajectories. As in what I told, these trajectories are almost identical. So dynamical phases collected on these trajectories are the same. Aronoff-Bohm phases collected are opposite because this loop is passed in 2 opposite directions. And in this case, the dynamical phase cancels. It's not there anymore. It results also in a different period. It's periodic with a period phi naught. Let us see. Ha! Nice equation. That's how to solve it. Right. We look at the solution. Oh, there's a simple analytical formula at some stage. Here plot versus flux. solutions at certain dynamical phases, and I have a period of 2 times phi naught. If I now average all these trajectories over dynamical phases, I will have this violet curve, purple curve, sorry, which oscillates with a double period. So there is a result of interference. What a pity, I have to stop now. If I had 2 more minutes, I would finally tell something about the experiment. But let us postpone it till the last lecture. Thank you for your attention.
Thanks.
Okay. Thank you.